So we're going to continue looking at section 5.1. So we left off yesterday with converting from polar to rectangular. Now we're gonna reverse it. We're gonna convert rectangular to polar. Okay, so first thing we need to remember is what we're looking for and what they give me. If we have a point that's in rectangular, what do we call the two values that they give you? Yep. Okay, so they're going to give you the x and they're going to give you the y. And if you want to change it to polar, what do we call the two things that you need there? Yep. Yep, the radius and the angle. Okay, so this is the reverse of what we did at the end of class yesterday. Okay, so they're going to give you the x and the y. That means you're going to know how far over you need to go. That's your x. And then how far up you need to go. That's your y. So you're going to know those two numbers. This point, let me draw it so you can see it again. That point right there, think of it, if you want to think of it on a circle like that, think of it as being right there. The radius is going to be from that point to where? How would I draw my radius there? Yeah, right from that point right to the middle, to the origin. So that's your radius. So we have to find that side somehow. So we'll talk about how to find that. And where would your angle be? Can you describe where in the triangle?
Opposite y.
Yeah, opposite y. There's your angle right there. So these are the two things we have to figure out. And the x and the y are what we're going to know. Well, let's start with r. If you knew x and you knew y, you'd know 2 out of 3 of the sides in that triangle. How can you always get the third side in a right triangle if you know 2 of them? Yep, we can do Pythagorean theorem. And I'm going to write this a little nicer on the next page. But really quick, the idea is that's how you find r. And I'm going to write this down nice and organized on the next page. That you do x squared plus y squared, and that's going to give you r squared. And you're going to know x and y. So Pythagorean theorem will get you r. Now, theta. You're going to know this side and that side. We need to know what position those two sides are in. What position is y relative to theta? Yep, that's opposite. And what position is x? That's adjacent. So we've got opposite, we've got adjacent. What trig function has those two? Tangent. So to solve for theta, we're going to have to use tangent somehow. Tangent equals opposite over adjacent. But that formula by itself doesn't really give me theta. It gives me the tangent of theta. My goal is to get just theta. So what do we have to do there to get just theta? Inverse. Yep, I'm going to have to take an inverse tangent. And I'm going to write that down on the next page. But that's kind of the idea of where the formulas are going to be coming from. We're going to use inverse tangent, because we know opposite and adjacent. And we're going to use Pythagorean theorem, because we know 2 out of 3 sides. That's how you figure out r and the theta. So first thing we need to figure out is what quadrant the point is in. Not so much for the r. For r, you can always just use the Pythagorean theorem. But for theta, it does depend on the quadrant it's in. If you're in quadrants 1 and 4, You can use exactly the formula that we just wrote down. The inverse tangent of y over x. That's exactly what we were getting at right here. If you take the inverse tangent of both sides. So that idea that we came up with works perfect if you're in quadrants 1 and 4. But what other quadrants could you be in besides those two? Yeah? You could be in 2 or 3. And the problem with inverse tangent is inverse tangent, when you type it in on the calculator, will always give you an answer between negative 90 and positive 90. Well, this is 0. Negative 90 is down here. Positive 90 is up there. So if inverse tangent always gives you an answer between negative 90 and 90, you're always going to be stuck in quadrants 1 and 4. But not every single coordinate you graph is in quadrants 1 and 4. You could get one in 2 and 3. So we've got to adjust this formula if we're not in quadrants 1 and 4. So if you're not in quadrants 1 or 4, not a huge change to it. All you have to do is add 180 if you're working in degrees, or pi if you're working in radians. That's the change to how you find the angle if you're in quadrants 2 or 3. Don't add 180 if you're in quadrants 1 or 4. You don't do that. Now, even these formulas, there's somewhere else that you could be besides quadrants 1, 2, 3, or 4. Where else can you end up?
On the axis.
You could end up on an axis. Now, think about what would happen if you were on an axis. Let's say you were right here. What's the x value of that point? 0. And the y value, I don't know. Maybe it's up 3, maybe it's up 4, 5, who cares? But the point is the x value is 0. Now, if you try to plug in an x value of 0 into either one of those formulas, what's going to happen?
You're going to get a 0 or a 1.
Which one? One of those, not both.
You can get either one, but you can put the 0 on the top or bottom.
Well, in this case, specifically, x is 0. You can't. You get undefined, right? So if you try to use this formula when you're on the vertical axis, you're going to be trying to plug a 0 into the bottom of this fraction. It doesn't work. So what you have to do is, if you're on the axis, you just have to memorize what this answer is. Whenever you're on the vertical axis up, what angle are you at right here?
90.
That's always 90. And if you're on the vertical axis but you went down, what's that one?
270.
That's 270. And if you go right, that's 0. And if you go left, 180. So these 4 angles, they're like special cases. So you got to remember, if your coordinate lands on an axis, you're not in a quadrant. So these formulas don't apply. You're either 0, 90, 180, or 270. So now that covers everything that could happen. Whether you're in quadrant 1, 2, 3, or 4, or you are on an axis. So that takes care of the angle. And what's the other thing that we need in polar besides the angle? We need the radius. And how did we say we were going to find that? Right. The radius is the hypotenuse of a triangle. I'll go back to this picture. X is the base, y is the height. Plug those two numbers into Pythagorean theorem, and you'll get the radius. And that formula works all the time. It doesn't matter what quadrant you're in. You don't have to do anything special if you're in a different quadrant. Okay, so those formulas are how you find your angle. All that. And that's how you find your radius. So we'll try a couple examples converting two polar. And then we'll have covered both ways, converting two polar and then converting two rectangular we did yesterday. So it says convert -2 to polar. Well, if they're telling me to convert two polar, then we know that that must be what? It must be the rectangular coordinate, which means this is a x and this is a y. So we know the x and the y. Okay, so the first thing is determine the quadrant, so then you can figure out are you using the top formula or the bottom formula. So let's determine the quadrant. It doesn't have to really be a perfect sketch, but we're just roughly trying to figure it out. You can even do this part in your head. So, Brady, what quadrant is that going to be in? Yeah, it's going to be right 2, down 2, so you're going to end up in quadrant 4. Any question on why it's quadrant 4? Right about there. Okay. So let's start with theta. What's my formula to find theta if I am in quadrant 4? Yeah.
Inverse tangent. Okay.
Yes. You do not need to add 180. Or if you were working in radians, it would be pi. Don't do that here. Okay, so inverse tangent. And then fill in your two numbers, y over x. -2 over 2. If I want, when I type in inverse tangent, what's -2 divided by 2?
Negative.
Yes, I'm just going to do the inverse tangent of -1. And that gives me an angle of -45 degrees. That's going this way. Now yesterday we went over 4 different ways, up to 4 different ways you can write a point in polar. I'm not going to go through all 4. But what if they did ask you, instead of going clockwise, they wanted it the other way, counterclockwise? What's -45 the same as? Instead of going this way, going the other way. 315. How do you get 315? Yeah, you just take away 45 from 360 or add 360 to that, it's the same thing. Brings you the other way. Which answer is right? Both. The only thing would be is if the directions say write your answer with a positive angle, well then you got to go with 315. All right, now we need our radius. So you can think of your radius as being the hypotenuse of a triangle. So this side is 2, and that side is 2. And you're solving for that. Sam, can you set up my formula to find my radius?
4 squared equals 2 squared times, or r squared equals 2 squared plus -2 squared.
Yep, so 2 squared plus -2 squared. So now we'll simplify that. Jenna, what's 2 squared plus -2 squared?
2. Oh, wait. Is it 0? Or 8?
One of those numbers.
It's 8.
It's 8, yeah. So 2 squared is 4, -2 squared is 4. So we end up with r squared equals 8. And how about, Tony, what do we do now to get r by itself?
You square root again.
So r is the square root of 8. And what does the square root of 8 simplify to? I don't mean write it as a decimal, I just mean like reduce it. It's something with square roots. This one will not be a fraction though.
2 square root 2.
2 square root 2. There's lots of different ways you can simplify square roots. We're not really going through that specifically, but one way I do it is I break 8 up into 4 times 2. So the square root of 8 is the square root of 4 times the square root of 2. But the key is when you break up 8, you've got to pick a number that you can take the square root of easily in your head. And that's why I picked square root of 4. Okay, so 2 square roots of 2. That's your radius. Okay, so now just write your final answer. Final answer should be radius, comma, and put your angle. So radius, angle. And save it. Any question on that one? To convert to polar, it doesn't really get any more difficult than that. Let's see. Let's try this. Okay, -4, -5. So, first thing is, what quadrant are we going to be in this time? Yeah. So we're going to go left 4, up 5, somewhere right above. Okay, so we know the quadrant. That allows us to pick the right formula for theta. Thanks. Yes, when you looked at me, I realized I did that wrong. Sorry about that. So yeah, quadrant 3, you were right. I put it in the wrong spot. So left 4, down 5. What's the formula that we use to find theta in the third quadrant? It's not the same as the one we just used.
180 plus y.
So 180 plus the inverse tangent. Difference is the plus 180. If you wanted to do it in radians, you would replace 180 with pi. So 180 plus inverse tangent y over x. Since they're both negative, they're going to cancel out when you divide. -5 divided by -4. So I'm just going to write +5 over +4. And that's not going to come out to a nice answer. So if we get an angle that doesn't come out nice, we'll just round it to 2 decimal places. So 180 plus inverse tangent of 5/4. So it's 231.34. Now, since we rounded the angle, we might as well round the radius. It doesn't make sense to write the radius as a square root as an exact answer, because we already have something that's not exact. So if we're going to use decimals, let's just use decimals for all of it. Okay. Now we got to find the radius. So we went left 4, down 5. So find your hypotenuse. 1. Can you set up my Pythagorean theorem to find the hypotenuse with sides of 4 and 5?
4 squared plus 5 squared equals 2 squared.
So 5 squared. And what are we using in place of c? Because this is really the distance from the center to the edge of the circle. We're just not calling it c. Yeah?
The radius.
The radius. We're calling it r because you want to think of it as if this helps. Think of it like that. It's on a circle, a certain number of units out. Okay, so that's going to give me 16. 4 squared is 16. 5 squared is 25. 16 and 25 is going to give me 41. And last step to get r by itself. Square root. If we were going to do this as an exact answer, I would just leave it as the square root of 41. But since we already have a decimal here, we'll just make that a decimal as well. Okay, so square root of 41. Okay, 6.40. Okay, you've got your radius, you've got your angle, just put it together and write your final answer. Radius, comma, angle. And this time, the angle came out positive automatically. I would say on the test, most of the time, that's what they're going to be looking for, a positive angle. Any questions on how we changed that point in rectangular to polar? Yep.
So on the test, if we do decimal for the angle, would we still do the angle like decimal for radius?
Yeah, I would say once you start using decimals here, I'm going to probably just let you use it for the whole problem.
Okay.
Yeah. If I say to write your answer as an exact answer, then I'd be looking for something more like this. That's exact. That's not a decimal. So it depends if the angle comes out nice or not, whether or not I'd let you do a decimal.
So on the test, you also want multiple positive angles?
Generally, it's going to be positive angles, but the directions will be the same. Yeah, I'd say generally positive angles. And that's the end of 5.1. So any questions on that? All right. So this is kind of the intro to A4. So remember, if you downloaded the whole book, A4 is in the back. The PDF is in the same spot. You'll find it for the homework, so you won't have to search for it. There's 2 PDFs for tonight's homework, because the first set of problems are going to be on this, and the second set are going to be on this. But they should both be together. All right, so what we're going to be looking at in A4 is a review of complex numbers. So first thing I like to do is just kind of figure out where complex numbers fit into the kind of numbers you already know. Okay, what are they? So I'm going to start with the simplest kind of numbers, and I'm going to work my way out to bigger and bigger sets that include more complicated kinds of numbers. So let's start right here. What's one of the simplest things you can do that uses numbers? Something somebody in like kindergarten might do with numbers. Count. Right? Counting. Simplest thing you can really do. And when you count, what do you start with? 1. So you don't include 0. There is no 0 in what we call counting numbers. And then the next number after 1 would be 2. There's also no decimals. So counting numbers include numbers 1 and up. No decimals, no fractions. 1, 2, 3, 4, 5, 6. The problem with just using counting numbers is when we get into arithmetic. Addition isn't a problem. You could give me a counting number. Somebody else could give me a different counting number. I can add the two together, and the answer I get will be a counting number. But with subtraction, we could have an issue. Somebody give me a counting number. 6. Okay. Well, let's say I did 6 minus 6. Everybody agrees 6 is a counting number, right? So I did a counting number minus a counting number. But the problem is the answer I get, it's not a counting number. So now what do? We don't have anything in this number set that represents the answer to this problem. So if all that you understood was counting numbers, you'd have to tell me that 6 minus 6 is like undefined. because you don't know how to say it. But we know how to say it, and that's the next number set. Those are called whole numbers. And with whole numbers, the only difference is now you have a 0. Counting numbers, 0 doesn't exist. Whole numbers, it does. So that is not a problem anymore. But there are other kinds of arithmetic problems we could still have an issue with. Somebody give me another counting number. 7. Let's do 6 minus 7. Everybody agrees 6 is a counting number?
Yeah.
7 is a counting number?
Yeah.
Yeah. So I'm doing a counting number minus a counting number, but the answer is not a counting number. So if you showed that to, maybe somebody in like first grade, they'd say, you can't do that. You can't have the bigger number come after the smaller number. It has to be the other way around. Well, it technically doesn't have to be the other way around. You can do that. We just get into a kind of numbers that have these symbols in front of them. Negatives. Once you introduce negatives into your realm of numbers that you understand, those are called integers. So now with integers, you can add, you can subtract, and you can multiply, and you'd never have an issue. You could give me any integer, somebody else could give me another integer, and I could add them, subtract them, or multiply them, and I would always get an integer for the answer. But there's another operation that can come up where you'd have a problem. Anybody know what operation I'm thinking of? What is it? A basic operation. Just a basic one. Division. Can you give me a counting number?
5.
5. And give me another one.
2.
2. Perfect. So if I take 5, which is a counting number, and I take 2, which is a counting number, I'm sorry, integer. 5 is an integer, 2 is an integer. And if I divide them, do I get an integer? No, integers don't include fractions or decimals. Integers only include numbers that don't have decimals. Positives and negatives, that's all they include. So if you gave that to somebody who doesn't understand decimals, they'd say, you can't do that. It's like if I had 5, markers and I want to give them to 2 people equally. Like, I can't do that. I can't take 5 things and distribute them to 2 people equally. The only way I can do that is if I start breaking things into pieces or parts, fractions. And that's rational numbers. So for most everyday kind of purposes, rational numbers is about as complicated as you would need to go. And rational numbers come up all the time. If you go to buy something, you put gas in your car, you might not put exactly 8 gallons of gas or 9 gallons of gas. If you just say, I want to put in $20, you might get, 5 or 6, whatever gallons. You're not going to necessarily get exactly a number. You might get in between 2 numbers. If you're cooking, right, you might not need 2 cups of flour. You might not need 3. You might need like 2 1/3 cups. So it's a fractional amount in between. Okay, so rational numbers come up a lot. When we start to move beyond rational numbers, that's when we start getting into numbers that are more abstract, numbers that people don't really use as much, the average person, in everyday life. Does anybody know what the opposite of rational numbers are? Yep, irrational. Now, when we get into irrational numbers, there's really a couple different examples. One example is a square root. Okay, if you take the square root of 5, that doesn't come out to a nice answer, and you cannot write that answer as a fraction. It's impossible. In fact, you can prove that it's impossible to write as a fraction. Thank you. And it's not like, well, maybe someday we'll figure out how to write square root of 5 as a fraction. No, we won't. It cannot be done, and it's provable. So what would you do with that? If it doesn't fit in the kinds of numbers that are fractions, which that's what rational numbers are, they're fractions, we got to put it somewhere. So we put it in this group called irrational. Another example would be something like pi. Pi is a number that you cannot write as a fraction. But square roots probably will come up most of the time. But even if you had a trade where you might use the square root of 2 for something, if you were doing some plumbing, and let's say you had to go around, you had an object here that's in the way, and you want to go around it, with your piping, and then continue. Well, it's going to take more pipe to go around that object than it is to just go straight through it. How much more is it going to take? Well, it depends on what kind of offset you do. But a lot of times you're going to need about 1.4 times the amount of pipe to go around it than if you went straight through it. And that 1.4 has to do with the number square root of 2. But for plumbing, you can use 1.4 and it's good enough. A lot of times pipes have a little bit of play in them. You can make it work. You don't have to measure your pipe, to the 100,000ths of an inch. That kind of accuracy isn't really needed for plumbing. Maybe if you're machining something for like a spaceship or something, you got to be a little more accurate, but not for this. So irrational numbers, at some point, most people just round them off, and it's good enough. You don't need to keep going forever. Let's see. If you take all the numbers that you can write as fractions, and then all the numbers that you can't, those are the kind of numbers you study in Algebra 1. Those are called real numbers. Well, just like when I had something like that, and I said like maybe somebody in like first grade wouldn't understand that, because you can't take away more than you have. We know you can. Well, if I gave that to someone in Algebra 1 and said, what's the square root of -4? They may try to type it in on the calculator, and it says error. Well, actually, it says error, non-real answer. It doesn't mean that you can't do this problem. It just means that the answer you get when you do it is not an answer that's in the real number system. It's an answer that's outside the real number system. And that's called imaginary. So if I press mode, and then I change the mode on the calculator, what I'm basically doing now is I just taught the calculator Algebra 2. So now it's not going to say that it can't do the square root of -4. It's going to know how to do it, and it's going to call it 2i. So each time that a number system is invented, whether it's a negative number or a fraction, it's because, at some point somebody had to figure out an answer to a problem, and there didn't exist some way to write it, so they invented a way to do it. And they got everybody else to agree to use it. That's how you do it. So now, if you take all these numbers, that's everything we have on the board. All the numbers that are reals and imaginaries, those are called complex numbers. Is there anything bigger than that? Is there something outside the complex number system? Going a little bit beyond what I'm familiar with, so that's as much as I know. So complex numbers is like the biggest category. And that's what we're going to look at in section A4. So the biggest thing you can see from this diagram is complex numbers have two parts to them. They have a real part, and they have an imaginary part. And the way that you write a complex number is exactly like that. You put the real part of the number first, and the imaginary part of the number second. If you write it in that form, that's called standard. And there's an example of a complex number. in that number that I wrote down, 2 plus 3i, we would say that the real part is 2. And the imaginary part is 3. So the real part is 2. And the imaginary part is the number in front of the I. That's 3. Now, not every complex number has a real part and an imaginary part. So when I teach Algebra 1, if we're doing a problem and the answer comes out to like x equals 2, and we solve an equation and that's what we get. That's a complex number. What that really means is the real part is 2, and the imaginary part is 0. Well, we try not to confuse people in Algebra 1 because they're just learning it, so we don't put that the imaginary part is 0, even though that's what it really means. So if one of the parts of your number is 0, usually we just leave it off. We don't write it. Okay. But if it's not 0, then yeah, you have to write it. Otherwise, how would somebody know what it is if you don't write it? But if it's not there, you assume it's 0. So just like not every complex number has to have an imaginary part, not every complex number has to have a real part. 4i. You could think of that as 0 plus 4i. There is no real part, and the imaginary part is 4. Again, if there's no real part, you're probably not going to see that written. They're going to leave it off. So that's called a pure imaginary number, 4i. Yeah, negative 2i. That's another. Any questions on that? So as far as applications of complex numbers, that gets pretty advanced. I mean, look at the box you're working in. Right? Rational numbers are what people mostly use in everyday life. Fractions, part of a dollar, cooking, in between things. Imaginary and complex numbers, I mean, it's way more complicated. So we don't, in this class, focus on applications. The only thing we do with imaginary numbers is learn how to add, subtract, multiply, and divide. Basic arithmetic with them. You can look up the applications for complex numbers, and I've looked it up. Every time I look it up, I'm always more confused than I started. So it's mostly engineering, but I'm not an engineer. If they could somehow be used in computer well, actually, they can be used in computer programming. You can draw something called a fractal. I don't know if you know what a fractal is, but if you Google fractal, they're pretty neat pictures. And I know imaginary numbers are used in drawing fractals. But as far as like other uses, like in engineering, I don't know the engineering uses. Bless you. All right. So what does it mean for two complex numbers to be equal? Well, let's say you had these two complex numbers. This is the first one. This is the second one. Each one of those numbers has a real part, and each one of those numbers has an imaginary part. If those two complex numbers are equal to each other, then you're telling me that the real part and the real part match, and the imaginary part and the imaginary part match. So for complex numbers to be equal, there are two things that have to match, not just one thing, two. So like that. Real part 3, real part 3. Those are equal. Imaginary part positive 8, imaginary part positive 8. Those are equal. We would say that those two complex numbers are equal. Now if you did this, they both have a real part of 3. One has an imaginary part of positive 8, one's negative 8. Those aren't equal. And you can't say, well, they're half equal. No, they're just not equal. They have to have the same real and imaginary parts in both to be considered the same number. There's no such thing as being kind of equal. It doesn't work that way. All right. So how do we add together two different complex numbers in a problem that might look something like one of these. Well, the idea when you add complex numbers, this is a real, that's a real. Combine like terms. That's how you do it. A and C get added together, and then B is imaginary, D is imaginary. Those get added together. And make sure you put an I next to the B plus D, so that way we remember that was the imaginary part. So real numbers can be combined with real numbers, and imaginaries get combined with imaginaries. All right, so let's try looking at a problem where we add two complex numbers together. And all we're going to do for today is add and subtract. All right, so we've got 3 plus 8i and 8 plus 2i. What's the real part of the first number? Let's see. First? 3. And what's the real part of the second number? Yep. 8. And the operation we want to do is addition. So what do you get when you add those up? 11. So that's going to be the real part of your complex number. Try to make your ones look different than i's, because otherwise things get confusing quickly. So the real part is 11. And then in this one, the imaginary part is 8. In this one, it's 2. And the operation is addition. So what am I going to get for an imaginary part in the final answer? 10i. So plus 10i. Okay, so 11 plus 10i. Let's try another one. So 4 minus 2i. And then I want to add 3 minus 8i. When I add those together, what's going to be the real part? 7. So you got 4 and 3, which are going to combine to give me 7. And what about, Jackson, what about the imaginary part?
You would combine it to negative 10.
Negative 10i. It's a negative 2 added to negative 8. So negative 10i. So that's that one. Let's try this one. So negative 3 minus 4i. And I want to add negative 7 plus 8i. So when I add those up, what's going to be the real part? Negative 10, good. And what about the imaginary part? Negative 4i combined with 8i. Yeah. 4i. There you go. So negative 10 plus 4i. Any question on that? Okay, so that's adding. Well, subtracting is really pretty similar. The difference is, you have to distribute the negative. So when you have a complex number that's being subtracted, whatever you have, in, whatever minus sign you have here, you've got to distribute it to the C and to the D. So what you end up doing is A minus C. That's how those are going to combine. And then B minus D. Remember, with the B minus D, put an I next to it. So we remember that that was the imaginary part. let's try a couple examples where we subtract complex numbers. So we got 4 plus 12i, and we're going to subtract 3 plus 4i. So remember, make sure that negative in front is applied to both the 3 and the 4i when we subtract. Okay, so what's going to be the real part when you subtract those complex numbers? 4 is the real part, minus 3 is going to give me 1. And what about the imaginary part? 8i. Yep. So 12i minus 4i. You've got to remember to subtract both. Okay. So 12i minus 4i, 8i. Question on that one? And this one. So 3 minus 5i, and I want to subtract 8 minus 6i. Same rules apply as with regular subtraction. If you subtract a negative, minus minus becomes a plus. Keep that in mind. What's going to be my real part here? Yep. 3 minus 8 is negative 5. Now, what about the imaginary part? Just be careful, because it's negative 5i minus 6i. So negative 5i minus 6i. What did we say happens to that minus and minus? It becomes a plus. So it's like negative 5i plus 6i, which is I. You can put 1i, or you can just put I. It's the same thing. Most of the time when it's a 1, people just put I. So any question on that? So we've been writing down I all over the place. I. All these different I's. Well, what is I? What do you think it is? Can you be more specific? What do you think if you ask someone in first grade, what do you call this? What would they say this type of thing is called? Or like this kind of thing, or this thing, or this thing? I don't think they would say it's a variable. I think they would say it's a letter. Now, that's what most people would think I is. And if I showed you something like this, that's a letter as well. It's not a letter in the English alphabet, but it is a letter in the Greek alphabet. It's the letter pi. Well, in math, do we ever use this as a letter? No, because it means something else. What does this mean? It means, what number? 3.14, right? If you were doing a word problem about like the number of pencils or something, you would never use pi to represent the number of unknown pencils, even though it begins with P. It's not a letter in math. Same thing with this. When we're talking about I in the context of this lesson, I is not a letter. Yes, it is a letter in the English alphabet, but in math, it stands for something. Just like that stands for something. So we would never use I as a variable in this section. I is a number. What number is it? It's that number. It's the square root of negative 1. If you try to type that in on the calculator, square root of negative 1, on a calculator that can do imaginary numbers, it will tell you that the square root of negative 1 is I. So now the question is I. Why is the square root of negative 1 I? Well, I can't tell you why. And there's no way that I can prove to you why that's true. That would be like me proving to you that parallel lines don't cross. I can't. When you say parallel lines don't cross, that's just what it is. It's like it's called a postulate. What's it called? I think it's called a postulate. It's basically something that you accept as being true and you can't prove, because you can't prove everything in the world. You got to start with something, and then you can build on that. And that's what this is. Somebody tried to take the square root of negative 1 on like a regular calculator. I'm just making this up. They got error, so they're like, what am I going to call it? I don't know, we'll call it I. And then everybody decided to use the letter I to represent the square root of negative 1. Okay, so that's a definition. You cannot prove why that's true. What it is. Like, why are stop signs red? I don't know. Somebody decided to make them red, and that's what it is. So now, I want to think about I squared. That I can prove to you what it is, based on the definition of I. Well, what did we just say I is?
Negative 1.
So it's the square root of negative 1. That's I. Multiplied by itself. Squared. What happens when you square and square root something? It cancels out. So what are you left with? You're left with negative 1. And that's an important idea, because we're going to do some arithmetic tomorrow with multiplying, where we might get an I squared in the problem. Whenever you get an I squared, you do not want to leave that in the problem. You need to change I squared to the number negative 1. So kind of like if you had this. If you multiplied those together, it would be 6I squared. Not add them. If you add them, it would be 5I. But if you multiply them, it's 6I squared. But I just told you that I squared is what number? So that's what it really means. It's really negative 6. So sometimes when we do arithmetic with complex numbers, the I disappears completely, and it's not even in the final answer. So that's what we're going to look at more tomorrow. That I squared turns into negative 1. And we'll do that with multiplication and division. Okay. So any questions on that? Alright, so as I said before, the homework is on 2 pages. Okay, the first page, I think it's 2. It might be 1 PDF with 2 pages in it, or it might be 2 PDFs, but it's all in the same folder. Page 308, 55 to 65, that's on converting rectangular to polar. And page 560, 9 to 14, that's on adding and subtracting complex numbers. Okay, so we'll finish section A4 tomorrow.